Hey guys. So, yesterday we talked about resonance and some of those advanced Lewis structures and formal charges. Now, remember, formal charges is really just where do the electrons belong? Who actually owns those electrons? Like I said before, if you ask my wife how many cars does she have, she's going to say two. You ask me how many cars do I have, I'm going to say two. And if, but in reality, we don't have four cars at our house. We have two. We have two cars. We share two cars. But if, God forbid, we were to actually split up and get divorced, one of the cars is in my name, and the other car is in her name. So, in reality, I don't have two cars. I have one car, and my wife has one car, and we share those cars. So oxidation numbers are just a way of going through and saying who actually owns what. Who actually owns these electrons. So that's kind of what oxidation numbers are going to be. We kind of did that with formal charges as well. Oxidation numbers are really here for ionic compounds, and they're going to be very useful later on in something called reduction and oxidation reactions. We're not going to get into that honestly at all in pre-AP, but this is a skill that you guys need to have for AP. Once we get into AP, this will really start kicking off. So I'm going to give you an example of how to calculate these oxidation numbers, then kind of show you a little bit why we're doing oxidation numbers, and then finally I'm going to give you a problem set to do. These are pretty simple. If you can handle formal charges, oxidation numbers are pretty simple. So again, if a compound splits up, some of the atoms keep more of the electrons than the others. Who keeps these shared electrons, right? So you have some kind of chemical reaction here where we have carbon tetrabromide, and it splits up into elemental carbon, pure carbon, and two bromine molecules. Remember, this is diatomic. It's two. So this is both elemental carbon and elemental bromine. All right. So who gets to keep these? Well, like many things in chemistry, we have a set of rules. Here are the set of rules. Now, don't go running and screaming. These are pretty simple rules to follow. Let me kind of just walk you through them. So, the oxidation number of a free element is always going to be 0. So, for example, that carbon that I talked about before, if it's just pure carbon and nothing else, this oxidation number, 0. There we go. It doesn't own more or less electrons than its typical valence electrons. All right. The oxidation number of a monatomic ion equals the charge of the monatomic ion. So in other words, if I said O2 minus, that's a tiny 2 minus, O2 minus, what's the oxidation number of this? Well, it's negative 2. There you go, negative 2. All right, that's pretty simple, right? If I said sodium ion, what's the oxidation number of a sodium ion? Positive 1. Positive 1. All right, number 3. The oxidation number of hydrogen is going to be +1. It's going to be +1. Unless it is combined with something that's less electronegative than it. It doesn't happen very often, but when it does, usually this is something like one of those group 1 or 2 metals, the alkali or alkaline earth metals, something like potassium. If you have potassium with hydrogen, which one of these is the cation, which one's the anion, which one's positive, which one's negative? The potassium here is going to be your positive cation, and that makes this hydrogen the negative ion. So the name of this is going to be potassium hydride. Remember, for the negative ions, you drop the back part of the name and add "ide." So potassium hydride. So in that type of situation, you can kind of tell this hydrogen is going to have an oxidation number of -1. All right. There's that. All right. Now, the oxidation number of oxygen. This is going to be very, very, very common. Oxidation number of oxygen in compounds is typically going to be -2, just like its monatomic ion, right? There is one exception to this, and this is one of those, exceptions that come up all the time on exams because they need to test the exception. So it's -1 in peroxides. Now, I don't even think we've talked about peroxides yet. What is a peroxide? A peroxide is this boy. Okay, this is something you probably have messed around with before in the past. Hydrogen peroxide. You might pour it on a cut or something like that, and it might bubble up. You might remember seeing that if you had a scrape. So in this case, when you have a molecule with oxygen bound to oxygen, both of these are going to be -1. Okay, and then hydrogens are going to be +1. There we go. All right. All right. Oxidation number of group 1 is +1. Group 2, +2. 17, -1. This kind of just makes sense, right? You can kind of remember, what's the charge of your group 1s? +1. What's the charge of your group 2s? +3. Or +2. +3? No, +2. What's the charge of your group 17? -1. So, as far as oxidation goes, these guys are pretty straightforward. And then last one, if you were to sum all of these oxidation numbers together, it should be 0 for a neutral compound. This kind of just balance your charges. That's really kind of what we're doing here. And then the last thing, sum the oxidation numbers of polyatomic ions should be equal to the charge of the ion. So you guys might remember that polyatomic ion nitrate, NO3 minus. So this NO3 minus, if you were to look at the the oxidation numbers of these guys, it should equal up to -1. There you go. That's that. All right, let's kind of put this into practice. Okay. Here's some examples. First one, let's go ahead and do it. NO3. This is kind of how I do it. I kind of run this kind of like Sudoku. I have my molecule, NO3 minus, right? I know that this top part up here is where I'm going to write my oxidation numbers. Oxidation numbers. Down here is going to be my what element, the total sum for each element. There we go. And then here, and this is going to be just my total. This will make sense in just a moment. So this is what I do. I go through and I think about my rules. My rules don't really talk about nitrogen very much, but they do talk about oxygen. Oxygen is going to be -2. So we know that the oxidation number for this oxygen is -2. Great. So I know it's going to be -2, but I got 3 of them. So that means in total, I'm going to have -6. Right? 3 -2s is going to be -6. Okay. So there's that. Now, I'm going to have a total of -7 because we have a negative charge here. Oh, I'm sorry. Nope. We're going to have a total of -6, and this needs to equal out to -1. So if we have a -6, we need to get it to equal -1 because it's an ion. what does the total positive side have to be? Well, it needs to be positive 5. Positive 5 minus 6 is minus 1. All right. So that means all the nitrogens have to be 5. Well, we only have one nitrogen, so that means that this guy has an oxidation number of plus 5. There we go. That is how we go about assigning oxidation numbers. You can do this pretty quickly. I did this entire little Sudoku thing because you can get a little complicated. It might get a little complicated with something like this guy. But, yeah, anyway. All right. Next one, oxygen in O2. So I'm going to draw out my Lewis structure of O2. There's my Lewis structure. All right. Well, here's the thing. This is elemental oxygen. This is how oxygen is. It's one of those diatomic molecules. And if you remember, oxidation number of a free element is always 0. So in this case, it's going to be 0. Done. All right. And now sulfur in sulfuric acid. So I'm going to write out my thing. SO4. There we go. Now, we kind of think back on these rules. Well, we know what oxygen is going to be. It's going to be -2. And each hydrogen is going to be +1. Okay? Don't know what this sulfur is going to be, though. Let's think. Let's kind of go through and do our little Sudoku thing. So we know there's going to be 4 oxygens at -2 apiece. So that's going to be -8. Okay. Hydrogens are +1. There's 2 of them, so it's going to be +2. All of this is going to equal the charge. Well, it's neutral, so it should equal 0. So what will sulfur be? Well, +2 minus 8, that should be +6. So the oxidation number for the sulfur is going to be +6. There we go. Not too shabby. Okay. Here were a bunch of practice problems that we were going to go through and do together. Let's see something. Let's do into O5. Let's do that one real quick. Okay. So, into O5. Same thing as before. Oxygen is going to be -2. There's 5 of them, so it's -10. All of this is going to equal 0 because this is a neutral compound. And then, so that means we need a +10 for nitrogen. There's 2 nitrogens, so nitrogen is, again, +5. There we go. So, here's some practice ones you want. I will say this. Oh, here's an example of when a hydrogen is in a compound with a less electronegative atom. So there's that. You can usually tell because the hydrogen is going to be on the back end of the formula. All right. So this is going to be really useful whenever we're dealing with transition metals. Those metals in the middle that can have multiple charges. That's kind of where it's nice and useful. Here's some nice, pretty transition metals. Okay, so here's the thing. This is about reduction and oxidation reactions. At this point, this is just kind of letting you know where it's going in the future. You won't actually be tested on this, but sometimes it's helpful to know why do we even care about these oxidation numbers? Well, this is why. We have a reaction like this. Okay, the question is, where are the electrons going? who owns these electrons, and why am I asking so many of these questions? Well, this is a thing where the electrons are getting shifted around. And we say if something is gaining electrons, it's a reduction reaction. And if it is a losing electrons, it is an oxidation reaction. The reason for this is a little bit of history. Back in the day, we didn't really know about electrons, but we did know about oxygen. And one way that these redox reactions actually work is by it moves electrons around, but it moves them with oxygen. Oxygen is very electronegative. So you're moving electrons around from one compound to another because you're moving oxygen around. So if you're being oxidized, usually you are losing electrons. And if you are being reduced as in you're losing oxygens, you're actually gaining electrons. All right, and here's a couple little mnemonics for it. Oil rig is kind of how I remember it. Oxidation is loss, reduction is gain. But what you can do is go through and assign your oxidation numbers to all of these things in the reaction. And you can see, oh wait, the manganese here and the manganese here went from a +4 to a +2. We're gaining electrons here. Here, it had a +4, or it is lacking 4 electrons, and now it's +2. It's lacking 2 electrons. It's gaining some electrons. And if that's the case, it's the reduction part of this. And then you can kind of look around, see what else is going on. This chlorine. This chlorine was -1, and it went to its free element, which is 0. So it went from a -1, electrons are negatively charged, to a 0, it lost electrons. And if it's losing electrons, then that's the oxidation step of this reaction. So this is you can kind of see what's happening here. Okay, if chlorine is losing electrons and the manganese is gaining electrons, you can kind of see, okay, so that's where the electrons are flowing from this thing to the manganese. And when we're talking about electrons flowing, you can start thinking about things like electricity and batteries. This is pretty much how batteries work. So if you're interested in being, the next Elon Musk and, designing the next electric car, which drives 10,000 miles and without a charge, then this is going to be your first step towards that, thinking about redox reactions. All right. Burp, burp. So you can kind of go through and see where the electrons are going. Okay. All right. So that's it. At the bottom of this video, or in the Canvas assignment where you see this, you'll see an assignment, a worksheet. Again, print it out, copy it, take a picture of it, submit it. You guys know what to do. All right. Have a good one, guys. Bye.